Hello everyone, my name is Dr. George. I will be taking you abstract algebra 1, and the topic we are going to be looking at this today is number theory. Number theory deals with the study of integers, and when we talk about the integers consist of the natural numbers together with their negatives and 0. So we begin this morning by looking at basic properties of integers, and the first property is the closure law of addition. That is, the set of integers satisfy closure law of addition. When you add two integers, you still get an integer. And the second one is commutative law of addition. Commutative law of addition. And we have the next one, associative law of addition. And the next one, number 4 here, is the existence of the identity element, additive identity. And the fifth one is the existence of additive inverse. Existence of additive inverse, that is, for every element A, and in the set of integer, there exists minus A, such that when you combine an element with its additive inverse, you are going to get the identity element. And the sixth one here is the closure law of multiplication for integers, and the next one is the commutative law of multiplication, and we have the associative law and the existence of multiplicative identity. And the last one here is the distributive property. Multiplication is distributive over addition. This one is left distributive. Multiplication is left distributive over addition, and we also have multiplication to be right distributive over addition. So those are the basic properties of the set of integers. And as we go on to today, we are going to be looking at how these properties are being used in some of the things we do. Now, we look at the principle of well ordering, and the principle of well ordering states that every non-empty subset of positive integers contains a least element. Every non-empty subset of positive integers contains the least element, a least element. Now, like for example, the set of natural numbers is well ordered, but the set of integers is not well ordered because it does not have a least element. So we begin by looking at some theorems, and the first theorem we look at is this theorem. If A divides B, okay, before that, let's look at what we call divisibility. Here in abstract algebra, when you say an integer A divides B, we write that like this: A divides B. And how do we express that mathematically? If A divides B, then we say B is equals to A times C. That is, there's an integer C such that B equals A times C. Like we say 2 divides 8. So that means that we can say 8 is equals to 2 times 4. So we look at some theorems on divisibility, and the first one is that if A divides B and B divides C, we want to show that A also divides C. So the first thing is to use this principle here. So now if A divides B, that implies that there is an integer C such that B equals A times T. And similarly, if B divides C, that means that there is an integer R such that C equals B times R. Now, what do we want to show? We want to show that A divides C. So let's try to have a connection between A and C. So from here we have a connection between A and B, and here C and B. So we can substitute B equals to 80 into this second equation, and we are going to have C is equals to B times R, that's equation 2, and instead of the B we write A times T, and this is the R here. Now we can use the associative law which we discussed earlier, and we have that to be A into bracket T times R. So T times R here is an integer, so we can represent that with another integer, because we've discussed what we call the closure law of multiplication for integers. That is, when you multiply two integers you still get an integer. So therefore we have C is equals to A into bracket T times R, where TR is an integer. So therefore A divides C. So the next theorem is, if A divides B, then A also divides B times C. We go the same way. If A divides B, that means that there is an integer D such that B, the one on your right here, is equals to A times an integer. So we have B is equals to AD. So we want to prove that A divides BC. So all we need to do is to multiply the equation by C. So we have B times C, that's BC, equals AD times C. So applying the associative law again, we have BC equals A into bracket D times C, and therefore we have what? A divides BC. A divides BC. We have the next theorem. If A divides B and A divides C, then we have to show that A divides BX plus CY. So there we go again. If A divides B, we are going to have B is equals to A times M, where M is an integer. And if A divides C, then we are going to have C is equals to A times N, where N is an integer. Now we want to show that A divides BX plus CY. So what we do is that we multiply this equation by X, so that we are going to have BX into bracket AM times X. And we can use the associative law again, so that will be A times MX. Now similarly, we multiply the second equation by Y, so we are going to have CY is equals to AN times Y, and using the associative law we have this. So we add BX and CY to get this, and we factor out A, so we get BX plus CY is equals to A into bracket MX plus NY. So MX is an integer, NY is an integer, so therefore we have A dividing what? BX plus CY. From this particular theorem we have two corollaries, and the first one is that an integer dividing two integers, we also divide their sum, and the second one is an integer dividing two integers divides their difference. Now that is easy to get from the theorem. So because we have proved that this theorem is true, so all we need to do is to put x is equals to 1 and y is equals to 1, and we are going to get the theorem will now change to, if A divides B and A divides C, then A divides B plus C. So that's the sum of the two integers. And similarly, an integer dividing two integers, we also divide their sum, their difference. So all we do again is to put x to be 1 and y to be minus 1, and then we get, if A divides B and A divides C, then A divides B minus C. Now we look at the next theorem, and the next theorem says that if A divides B and B divides A, show that A is equals to B, where A and B are natural numbers. I need to correct this. The first note I sent, we have, if A divides B, then there's an integer. Please, A and B are integers, so M here will be a natural number. A and B are natural numbers, so M here will also be a natural number. The same thing for T here. So let's go. If A divides B, don't forget A and B are natural numbers, then that means that there must be another natural number, m such that b, the one on your right here, is equals to a times that natural number m that you are introducing. So we have b is equals to am, and we have the same thing for if b divides a, and that means that there is a natural number t such that a is equals to b times t, where t is a natural number. Now we want to show that a equals to b. A equals to b. So how do we do that? So you look at your equation 4 and 5. So what you can do is that you can substitute either equation 4 into 5 or 5 into 4. So here we have substituted 4 into 5, so that we have a is equals to b, and b is now am. So we have am times t. So we have this equation. We can factor out a using the associative law on the right hand side of this equation. So we have a is equals to a into m times t, a into m times t using the associative law, and cancelling out, we have 1 is equals to m times t. 1 is equals to m times t. So don't forget, m and t are natural numbers, and since m and t are natural numbers, and when we talk about the set of natural numbers, we have 1, 2, 3, 4. So we see that m must be equals to 1 and t must also be equals to 1 for this equation 6 to be satisfied. So m must be 1 because 1 times 1 will give you 1. That's the only natural number that can satisfy this particular equation. So we have m times t equals to 1. So m must be 1 and t must be 1. So if we substitute that into either equation 4 or 5, we have a equals to b or b equals to a. Now, we have this theorem and we call it the division algorithm. The division algorithm says if you have two integers a and b, then there exists unique integers q and r, where q is called the quotient and r is called the remainder, such that we have a equals to b times q plus r, and 0 must be less than or equals to r less than b. So we call this the division algorithm. The division algorithm. We will see where the division algorithm is being used. We use it every time, and even this is the long division method we are used to, like when we are treating polynomials. So now quickly let's look at what we call the greatest common divisors. So greatest common divisor. So but before that, we look at what we call common divisor. Common divisor, if you have two integers a and b, and if c can divide a, c can go in, is a factor of a, and c is also a factor of b, so we write that c divides a. And if c also divides b, that means that c is a common divisor of a and b. So we can have so many common divisors of two particular integers. We can have so many of them, but the greatest among them is called the greatest common divisor. That is, if c is a common divisor of a and b, and if d can also divide a and b, then c will also divide d for d to be the greatest common divisor. Now, the greatest common divisor is what we call the HCF in our primary school days, and we can easily compute the HCF then. But here, when the value of the two integers, when the two integers we are talking about, we want to look at their common divisors. When they are large values, it might be difficult for us to use the method we are used to in primary school. So